Okay, here we go. Today, we're going to talk about probability functions some more. So before leaving section 12.2, well, we've been working these interesting problems where they're looking at numbers. More abstractly, let me list 8 general properties of a probability function. Well, first, let me remind you of the definition of a probability function that takes in 3 of the properties. Properties of a probability function. So, the definition. We defined a few days ago what qualified as a probability function. Well, let's assume we have some sample space. Assume it's, for the moment, a finite sample space. Call it omega, of course. The probability function assigns numbers to events, right? And an event is some subset of omega. So it's some function, we always call it P for probability, that assigns a number, of course written as P of A, to each event A, in such a way that 3 conditions hold. Well, those 3 conditions are the first of the 8 that I've referred to here. So let's write down those 3 conditions again. The number that's assigned to an event has got to be between 0 and 1. It makes no sense to talk about a negative probability or a probability greater than 1. And 2 talks about the 2 extreme cases. The probability of the impossible event, the event that has no members whatsoever, has got to be 0. And the probability of the certain event, the event consisting of all possible outcomes, has got to be 1. And then thirdly, if we have 2 events, A and B, and they don't overlap at all, then the probability of their union. So their union is the event that consists of all the outcomes where we have event A, or we have event B, or maybe both. And the probability has to be just the sum of the individual probabilities if A and B are disjoint. Where disjoint means they don't overlap, an equation form that's just their intersection. Their intersection is going to be an event. Consists of all the outcomes that are both in event A and B. Well, if they don't overlap, their intersection has nothing in it. Their intersection will be the impossible event. You already knew this. So what I want to write down are 5 consequences of these 3 properties. Okay, so we'll have 8 altogether. So we'll keep the same numbering going. So the first of these will be number 4. The probability of A complement. Well, by the complement, I mean the event consisting of all the outcomes that are not in A. Usual picture. The rectangle is omega. The circle is the event A. A complement consists of the outcomes not in A. So A is some event. A complement means that the event A does not occur. For example, if we happen to know that the probability that George is on the committee is 4/9, then without any further thinking, calculating, or even thinking very much, the probability of the complement, probability that George is not on the committee, is 1 minus 4/9, 5/9. And the reason you want to know this is that sometimes to find the probability of an event, it's easier to look at the complement to see how likely it is that the event does not occur. This can also be turned around, and the probability of an event A is 1 minus the probability of its complement. And if we know one of these, then by applying it to the complement, we can get the other version. And the reason this property is true, it follows from the things over here. A and A complement are disjoint. Right? There's no outcomes that could possibly belong to both. Okay, so A and A complement don't overlap. We can apply 3 to them. The probability of their union is the probability of A plus the probability of A. But what is their union? A complement has all the outcomes that aren't in A. So together, they make up the entire sample space omega. And by condition number 2, the probability of omega is 1. So that says the probability of A plus the probability of A complement is 1. Rearranging that equation gives us either of these. Gives us both of these. Now, what if we have 3 events? Well, if they don't overlap, we can get an improved version of condition 3. Okay, so we're up to number 5 now. What if we have these three events? A1, A2, A3, no two of which overlap. No two overlap. So any two of these are disjoint. So A1 and A2 are disjoint, A1 and A3 are disjoint, A2 and A3 are disjoint. Then if we apply property 3 twice, well, we get this version of A3, of property 3, that the probability of the union is going to be just the sum of the individual probabilities, provided that no two of those events overlap. So that the picture has to look something like this. That is, the intersection of any two of these would be empty, the impossible event. Well, we get this by applying the 3 twice, first for A1 and A2, and then we take that together with A3. No reason to stop here. What if instead of 3 events, we have n events? And we are interested in their union, the event consisting of, well, either the outcome is an A1 or A2 or maybe A sub n. Well, if any two of these are disjoint, well, we can write that down symbolically. We want to say any two of these are disjoint. Yeah. Any I and j that are different from 1 to n, the events have nothing in common. Well, then we get that equation for these n events. We'll talk in a minute about what to do if they're not all, if we have 2 events and they're not disjoint. But yeah, there's another way to write this equation. The right-hand side, this sum, of course, we can write with the sigma notation. Sum I equals 1 to n, probability of A sub I. As a way of writing the right-hand side. Now, what about the left-hand side? Well, there's a way to write that also by analogy to the sigma notation. We're looking at a union. As I goes from 1 to n, A sub I. Which means that union. Well, this lets us write down an improved version of condition 3 here. Let's call that version 3.1. For an infinite sample space. The definition of a probability function requires one additional condition. Now, we haven't done any problems with infinite sample spaces yet, but we will. a 3.2. It says, yeah, this has to work even if you have infinitely many events, no two of which overlap. So I equals 1 to infinity. Okay, so we write down if we have infinitely many disjoint events, okay, so A sub I can't overlap at all with A sub j. Well, so this finishes the definition of probability function even if the space is infinite. We have this improved version of 3.1. Okay, but let's make things simpler. We can apply number 5 here in the case where the events are singleton events. They just consist of one outcome. Let's put it the following way. Say we are interested in the event A, consists of the n different outcomes. Well, so we need names for the outcomes. Say T1, T2. There's n of them. So A is a set of outcomes. It's an event, a set of size n, and we have names for its members. Then the probability of A is a sum. It's the probability that T1 happens. Well, T1 is not an event, it's an outcome. The set consisting of T1 only, that's an event. So braces, it's an event, but it's kind of a small event. It just has this one outcome in it. The event that T1 happens and nothing else. Well, the set A consists of T1 and T2 and so forth. Probability of A is the probability that T1 happens or T2 happens. T1 and T2 are different, so these two singleton events don't overlap. Out to T sub n. And sometimes we use this without really thinking much about it. The probability of 3 outcomes. Well, we can look at the 3 outcomes one at a time and find the probability of each one and add them up. For example, suppose we are given the following numbers for flipping a coin twice. Now, this is not a fair coin. Oh. Warning, it's not a fair coin. Heads and tails are not equally likely. But we're given the following pieces of information. One possible outcome is that both flips come up heads. we're given that probability. Or maybe they both come up tails. We're given that. Or maybe we get first tails and then heads in that order. That's 2/9. We're given these three numbers. If we want to know the probability that the first flip is tails, well, that's the probability of a certain event. What event? Well, all the outcomes where the first flip is tails, so it consists of these two events. And the probability of this event, well, we just add the numbers we're given. And to be a purist, say there should be some braces here, but we'll sometimes leave them out. And we know these numbers, we just add them up. 2/9 and 1/9. And similarly, what's the probability that the second flip? Did I add that up wrong? Doesn't look right, does it? One of these numbers, that 1/9 there. Yeah, let's fix that. Thank you. That's 4/9. 2/3. How does that seem? Yeah, that looks better. 2/3. Okay, let's see if I can do this part B. Probability that the second flip is tails. Well, so now the event we're talking about has these two outcomes in it. We're told the probability of tails was 4/9. Probability of heads tails. Yeah, well, that's not listed here anywhere. Yeah, but we know the probability of its complement. That is, the event heads tails, that's the complement of everything else. Heads, heads, tails, 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 heads. And we can figure out the probability of this event just by adding up these three numbers. 1/9 plus 4/9 plus 2/9, 7/9. Well, if the probability of the event consisting of those three outcomes is 7/9, its complement has probability 2/9. We're back to 6/9. Yeah, given the probability of these 3 outcomes, when there's a total of 4 outcomes, we can fill in the missing number using property 4. Well, on to property 7. What if we have 2 events, but they're not disjoint, or not disjoint as far as we know? There's still a useful equation for the probability of their union. So this is to hold for any events, A and B. Maybe they overlap and maybe they don't. We want to look at the event A union B. That's the event where the outcome is either in A or in B or maybe in both. Well, if they don't overlap, property 3.1 tells us what happens. If they do overlap, we have to correct for this by subtracting off the probability that both events occurred. Because the things in the intersection here, yeah, they get counted twice if we do just add these numbers up. Picture, the rectangle is the sample space. Yeah, A and B might overlap, and it follows from these other properties we have that we can get the probability for the union in this by using this equation. So if we flip this unfair coin twice, we said the probability that the first flip is tails is 2/3. We said the probability that the second flip is tails. So the probability that one or the other event occurs, either the first or the second, or both, is tails, is, well, what it's not what we would get just by adding these numbers up. But that would give us a probability greater than 1, so we know that's not right. We can add those numbers up, but then we have to correct by subtracting off the probability that they're both tails. Well, so if the probability that they're both tails is 4/9, as it was over here, okay, so this is 2/3 plus 2/3, but then we have to subtract off 4/9 because that got double counted. Okay, so 4/3, that's 12/9. Subtract off 4/9, 8/9. But certainly it's something that's less than 1. And lastly, on this list of 8 before we go back to working problems. A simpler property. See, why does number 7 hold? Well, it relies on the fact that in this picture, those 3 regions are disjoint, and we can apply what we know to those and add things up. Okay, let's go back to number 8. If we have events A and B, and A is a subset of B. Okay, usual notation for a subset. That means all the outcomes in A are also in B. B might have some other outcomes, maybe not. But we have a picture. There's A. And A is sitting inside B. B might have some other things out here, maybe. But one thing we can say for sure is the probability of A is no larger than, so it's less than or equal to the probability of B. The reason that holds is we've got a couple of disjoint events here. We can look at B as made up of 2 parts. They're all the outcomes in A. And then the outcomes that might be in B, but not in A. Well, we have a way of writing that. Outcomes that are in B, and they're not in A, so they're an A complement. And these 2 events are disjoint, because nothing can be in both A and an A complement. So we can apply property 2. The probability of B is probability of A plus the probability of this funny looking thing here. And we don't really care what that is. But by property 1, it's non-negative. So the probability of B comes from the probability of A by adding something to it, which could be as small as 0, but it can't be any smaller than 0. And that gives us this inequality. Well, end of the list. Let's do a few more problems. Suppose our experiment consists of choosing a number, a whole number, at random from the interval from 1 to 100. We choose at random. By at random, I mean, all of the numbers are equally likely. A whole number, an integer, from the closed interval from 1 to 100. what's the probability that the number we get, the number we choose, turns out to be, well, it might be divisible by 2. Or divisible by 5. Or maybe both. Well, so let's see what the setup is here. The sample space can be thought of as just the set of all the whole numbers out of this interval. It's 1, 2. Well, it's too many. We don't want to write them all down because there's 100 of them. And they're all equally likely. So for the probability of an event, we just need to know how big the event is. Say t is the event of being divisible by 2. Okay, so t stands for 2. Well, so that's all the outcomes in the sample space that are divisible by 2, divisible evenly with 0 remainder. So that's all the even integers, from smallest of which is 2 and goes up to 100. All of these, but leaving out the odd numbers, which are not divisible by 2, because we'd get a remainder of 1. So there's 50 of these. So we know that the probability of t is a half, 50 over 100. Yeah, but that's not what the question asks about. We also need to look at the event of being divisible by 5. And there's a bunch of these numbers that are divisible by 5. Yeah, but how big a bunch? We'll call that event f for 5. Let f be the event that the number we choose is divisible by 5. So that's a set of outcomes. The smallest number divisible by 5 in the sample space is 5. Quotient of 1, a remainder of 0, but all the smaller ones give a non-zero remainder. And 10 and 15. There's a bunch of these. How big? Claim there's 20 of these. 1 times 5, 2 times 5, all the way up to 20 times 5. So the probability of getting a number divisible by 5 1/5. And what the problem asks for probability that the number is divisible by 2, or it's divisible by 5, or maybe both. That is, it's asking for the probability of this union. Well, one of those properties we've just listed tells us what that probability is. We take the probability of being divisible by 2, that was a half, plus the probability of being divisible by 5, that was 1/5. But then we have to correct make sure we don't double count the outcomes that are in both. So we'll need to subtract off the probability of being in both divisible by 2 and divisible by 5. Perhaps running this into the ground. The numbers from 1 to 100 that are divisible both by 2 and by 5, well, the first such number is 10, right? Because anything smaller would leave a remainder for one or the other. Numbers that are divisible both by 2 and by 5 are going to have to be divisible by 10. So there are 10 such numbers in the sample space. So the probability of being divisible by both is 1/10. Well, now if we put all the pieces together, okay, so we have 5/10 there, 2/10 there. We subtract off 1/10 to make sure we're not double counting. 6/10. 3/5. Yeah. There's a 60% probability that we'll get a number that's either divisible by 2 or by 5 or maybe both. Well, a different sort of question. Well, as we're talking about events, how many events are there? Well, it depends on how big the sample space is, of course. Let's start with a small sample space. Say the sample space has size 3. So it just consists of 3 outcomes. And we need names for the outcomes, call them A, B, and C. Let's list all the events. And that will tell us how many there are. Well, let's start at the top with a certain event, omega itself. That's an event. It's a set of outcomes. It's the only event of size 3 that there is for this sample space. Now let's list all the events of size 2. Well, so we'll have to leave out one of the outcomes. And so we get these 3 events of size 2, depending on whether we leave out C or B or A. But to get an event of size 2, Complement has to be of size 1. And now let's list all the events of size 1. Of course, there's 3 of those. And we're almost done. Almost, because we haven't listed yet the impossible event, the event of size 0. But any event has to be of size, well, no more than 3, so it has to be 0, 1, 2, or 3. Altogether, 8 events. Count them. 8. 1 and 3 and 3 and 1. Well, we could have predicted that. The number of events is 2 to the third. Because how many different ways can we make an event? Well, that's one of these counting problems. In fact, this has come up briefly before. We have these 3 outcomes. To make an event, we have to take some set of, any old set of outcomes. There are 3 tasks. We have to put A in the event or not in the event. 2 choices. We put A into the event or into the complement. Task number 2. Task number 3. Well, once we do all 3 tasks, we have an event. And any event is going to get produced by doing these 3 tasks somehow. By the multiplication principle. The number of ways to do all 3 tasks is 2 times 2 times 2. 2 to the third, that's 8. So the multiplication principle tells us ahead of time that the number of events is going to be 8. And sure enough, here's a list of all of them. There's 8. And to generalize this, if we know how big the sample space is, we know how many events there are. Say the sample space has n outcomes in it. There are 2 to the n different events altogether. Because the number of ways to make an event, well, you have to do those n tasks. Each task can be done in 2 ways. The number of ways to do all of them is 2 to the n. So if we have 7 outcomes, there are 2 to the 7th events. 2 to the 7th, that's 128 events. Well, we wouldn't want to list all of them unless we have a lot of time to kill. But for n outcomes, there's going to be 2 to the n events. Got to stop for this week. Come back on Monday.